Alrighty, promise you, no tricks. Today, of any day of Algebra 2, is the one day, if you can pay attention and you can understand the ideas that we're going to go over today, will be the most beneficial to your real life. Promise. So today we're going to start by talking about exponential growth. We're then going to talk about exponential decay, which is basically the same thing, just a little bit different, and I'll talk about how to differentiate between those two things. But the reason that exponential growth is so important is that this is how compounding interest works. So basically, if you understand compounding interest, you understand how your mortgage functions, you understand how your student loans accumulate, and you understand basically how to put yourself in either a good financial place or a bad financial place, depending on what debts you accrue and how you're able to pay them off. So that's why today is really important. Let's get into it. The first thing is when we're talking about exponential growth, all these exponential functions have a b value, which is the base, raised to an x. So we're going to keep things pretty simple. We're going to just leave it as x. You can do different, 2x, 3x, things like that, where it happens faster, but we're not going to do a ton of scaling stuff like that. So we're going to start out with just a very basic example, which is just 2 to the x. So in this example here, we're going to look at this and say, okay, our f of x, our function, which is the same thing as saying y equals 2 to the x, is going to be this graph here. We notice this graph gets really, really close to y equals 0 here, but it never actually touches it, and then it'll shoot off to infinity over here. The reason for this is no matter what value I raise to, I'm not going to be able to get it to turn negative. So let's say I plugged in a very big negative number. Let's say I plugged in negative 100. 2 to the negative 100 is just 1 over 2 to the 100. So that's just one massive fraction in the denominator. So that's just going to basically be 0, right? 1 over a million is basically 0. So when we're looking at these functions, when we plug in these values, we see it's going to reach an asymptote. And we'll talk about this asymptote more, but the asymptote is where the line is going to flatten out, or the curve, is going to flatten out towards a line. So when we're looking at these, we'll have an asymptote at k, which we're going to get into the more in-depth version of this, but just want to introduce it like this. We're also going to have a k factor, which will shift us up and down. We'll see that in a second as well. So just looking at this one here, basically it's starting at 0, and we've got this point, 0, 1. Whenever I have a number raised to 0, so 2 raised to 0, it is 1. So that'll be an important thing to keep in mind, is any number raised to 0 is 1. So as we're looking at these things, we're saying, okay, well, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So this thing grows very, very quickly, and that's called exponential growth. Now this thing trails off if we were to go in the other direction. It's not that it gets infinitely small, right? It doesn't get like to negative infinity, but it will approach 0, that y equals k value, which we'll see in a second. So 2 to the negative 1 is just 1/2. 2 to the negative 2 is 1 over 2 squared, so 1/4. And then likewise, 2 to the negative 3 is 1 over 8. So this is just our kind of introductory parent function sort of deal, looking at these things. Here is, oops, I guess I can scoot just a smidge down so I can include the asymptote here. So asymptote is this line behavior as it approaches right here. So again, as it approaches y equals 0, as x goes to negative infinity, we see that happening right here. And as x goes to positive infinity, it's just going to go to positive infinity. So these are only going to have an asymptote on one side. So this side of the equation, the right side of the equation, as x goes to positive infinity, is just going to go to positive infinity. So I'd say this part of the graph right here is just representing as x goes to positive infinity, that f of x will go to positive infinity. But then we get this part of the graph, which we see flattening off, and that is going to be as x goes to negative infinity, f of x is going to approach 0. So here we have this asymptote at y equals 0. So it's always going to be y equals and then whatever number k is here. Looking here, we want to just talk about the difference in these characteristics. So when we've got an a value out in front, this a value can either flip this thing or it can basically make it happen a little faster or slower. So I describe it kind of as like a stretch. So in terms of like a plain vanilla version of this thing, we'd say y equals a b to the x. B, again, is our base. to the x here is our exponent. So this a thing is either going to flip it up or down if it's positive or negative, but then beyond that, b to the x is going to do the driving. So again, it'll happen a little faster, a little slower. Like if a is 1/2, it'll happen a little bit slower. If a is 2, it'll happen a little bit faster. But other than that, it doesn't have a massive impact in terms of like generally describing this thing. So when we look at these, there's basically 4 options that I could have, and it's really just 2. So if my b value is less than 1, so let's say, for example, I had 1/2, actually I'll do a new color here. So let's say I had 1/2 raised to the x, okay? So this example is going to have a value that is less than 1 with a positive. Did I screw these things up? I think I screwed this thing up. Let's see here. Nope, no, I did it right. So, excuse me, I'm just reading it wrong because I'm silly. So here we have a b value greater than 1. So for b value greater than 1, let's take this one. And we're going to just scoot this downstairs because that's what we meant the whole time. So we'll choose a b value greater than 1. There is a 2 to the x. So here's an example of exponential growth. B value, again, 2 bigger than 1. So therefore, 2 raised to the x, which is positive, is going to be exponential growth. Now let's change this thing up. Let's say, okay, maybe I had 2 to the negative x. Now this thing turns into decay. The reason being is this is like saying 2 raised to the negative 1 raised to the x. 2 raised to the negative 1 is 1/2 to the x. So here we see this decay function, and here's our example, 1/2 to the x. B value between 0 and 1 raised to a positive exponent. This is decay. For our growth example, we'd have 1/2 raised to the negative x. Again, if I had 1 divided by, and then I'm going to say 1/2, that's like saying 2. So this is 2 to the x. So when we're looking at growth, again, b value is going to be greater than 1 and has a positive exponent for its x value. And then for decay, we have a b value less than 1 with a positive exponent. That's going to be decay. Or I can have a b value greater than 1 with a negative exponent. That's decay. B value of less than 1 and a negative exponent, and that'll turn into growth. So here's really the summary table for these different scenarios here. Now let's look at graphing a couple of them. I'm going to show you, let's see, yeah. So I'll show you these graphs, but then I'm going to show you kind of how I think about them. So in example 1 here, we're looking to graph this function. A value here is not yellow. That's a poor choice. Let's do this. A value equals 1/2. B value equals 3. My exponent is positive. Okay, so these are the things that I note for myself. This is bigger than 1. This is positive. Therefore, we have exponential growth. It doesn't matter there's a 1/2 in front of that thing, still fine. So when we're graphing this thing, I would encourage you to start with this point here. It's not that it's an actual vertex, like these don't really have a vertex, so to say, but I find this is a pretty good point to help orient ourselves and look at the interesting stuff, because a lot of it's just going to be crazy fast growth that we can't really even graph very well. So when we're looking at this, I would argue that we should start with h. I know we haven't introduced h here, but it's going to be in this exponent. So I guess I'll just flip to this for a second. So if I have a value in this exponent, it's going to shift it left or right. If it looks positive, it's actually going to be shifting to the left. If it looks negative, it's actually going to be shifting to the right because it's x minus h. So when we look at the k value, it's just going to be our vertical shift, and that's going to be up or down. If k is positive, it's up. K is negative, it's down. So when we're looking at these things, that's basically how it affects it. A does the flip and the stretch. So very similar to all the stuff we've seen so far before. And here's another little summary of whether it's exponential growth or decay. When we're talking about this thing, if the a value is less than 0, so basically just saying if I have a negative a value, then we don't actually refer to it as exponential growth or decay. It's just a negative graph. So a little kind of like, I don't know, underwhelming there, but it is what it is. The rest of it's fairly whelming for you. So as we look at this, we're looking at our vertex hk. So h, I don't have anything plus or minus with this x, so my h value here is actually going to be 0. And then I don't have anything plus or minus at the end of this equation, so my k value is actually equal to 0. But my a value here is 1/2. So here's where this 1/2 is going to come into play. So my starting point here is going to be 0, comma 1/2. And we see that on this graph right here. So I personally will start with this point, and then I'll move 2 to the right, and I'll include 2 points on the left as well. So when I'm graphing these functions, I will typically use 5 points. You can use less. It's just that from there, you're basically just going to be like ballparking it. Especially for students starting out, I don't recommend just using 2 points because this curve is not intuitive to you probably yet. Maybe it is, I don't know. But when we're looking at these things, if I just draw 2 points, usually what our brain wants to do is just draw a line through that. But these are definitely not linear. These are exponential. So that's how I would start. And then from there, I would, again, take 2 points to the left, 2 points to the right. So then I would plug in -1 and -2 and see what it spits out. And I would plug in 1 and 2 as well and see what I get there. So again, t-chart, just like we usually do here. So got x's, got our y's here. Since my h value is 0, that's where I'm going to center myself. -1, -2, 1, and 2. And then we're just plugging these values in. So 3 raised to the -2 is going to give me 1/9 because it's 1 over 3 squared. And I'm doing 1/2 of 1/9 because I've got this a value as well. So 1/2 of 1/9 is 1/18. Now I'm going to be doing 1/2 of 1/3, which is 1/6. For our 0, we said it was just going to be 1/2. 1/2 times 1, because 3 to the 0 is 1. For my 1 value here, I'm going to get 3/2, and then I'm going to get 9/2 here. So just plugging in these points, I don't know, I'll do one more kind of point on here. Let's do that point right there, which is that one. So just looking at these, there's an additional point for you. Don't worry about graphing these ones accurately. I mean, as long as it's between 0 and 1 or like fairly close to it, like those points, you know, how on earth would I ever be able to tell you graphing, you know, 1/18 versus 1/6? It's not going to happen. So as long as it looks fairly good and this arrow stops at this y equals 0 line, that's what I'm looking for. This arrow should not dip below because that's going to basically cross over the asymptote, which is not going to be a thing. It doesn't happen. So just keep that in mind when we're graphing things like this. For the one on the right here I have a negative a value. So since I see this negative out in front, this b value never going to be negative, okay? So b value is either between 0 and 1 or greater than 1. If my b value is 1, then it doesn't really do much. It's just 1 to the power, and it just ends up being a constant. It doesn't change anything. So when we're looking at these things, let's use blue here. A value is -1, h value is 0, k value is 0. My exponent here is positive. And now I want to look at, okay, well, here I have a b value of 3/2. Last time I checked, 3/2 was greater than 1. So I'm greater than 1 here, and I have a positive exponent, so I'm going to be doing exponential growth in theory. But then I look at this a value again, and I go, oh yeah, but it's -1. So since it's negative, it's not actually going to be exponential growth or decay. It's just going to basically be like exponential growth, but flipped over the axis, right? So flipped over this y equals 0. So when I look at this thing, I'm going to start with my h, which is 0, comma a plus k. So again, k value being 0, -1 plus 0 is going to be -1. So that's where I get this point here. From there, to the right, to the left. So here's one point to the right. One more point to the right would be somewhere around there. And we'll go one to the left. Oops. To the left. There we go. So again, setting up the same t-chart. I'm not going to go through and do it here because I feel like probably is fairly straightforward. I don't know. Maybe I should do it. The people love t-charts. We give the people what they want. Starting on 0, -1, -2, 1, and 2. So plugging in this value, we got -1. When I plug in -1, So 3 halves to the -1 is going to basically flip this fraction to 2/3. And so this is going to be negative 2/3. And here we're going to basically do the same thing again, but it's going to be squared. So I'm flipping this thing. Now it's going to be 4/9, and it's negative. Oops. Negative 4/9. There we go. For my 1 value, 3 halves to the first is just 3 halves. So this is going to be negative 3 halves. And I'm going to have that value squared. So this is now going to be negative 9/4. One thing you'll find is that when we're on a test or doing assignments like this, more often than not, we'll just round these things to 2 decimal places. Just make sure you read the instructions carefully. So a lot of this is just going to be approximations. 2 decimal places is typically how we'll roll. To graph this thing, we want to look at our h and k values. So here's where we get into the more detailed version. So again, A is the flip and stretch, H is horizontal shift, V is my vertical, K is my vertical shift. My vertex, quote unquote, is not a real vertex, but this is where I start the problem, is with H, comma, A plus K. The reason it's A plus K is that when I plug in H, B is going to cancel off here with whatever my X was that I just used for the H value. So this is going to give me a 0. B to the 0 is 1. So now it's going to be A times 1. So it's going to be whatever the A value is plus K. So that's why when I plug in H, it spits out A plus K. If you don't do that, basically you just run the risk of centering yourself on a point on the graph, which is fairly arbitrary. And so like what will happen is, say I had a graph like this, but I had it shifted over, 10 units to the left or whatever like that. So if I did that and you started at 0, you'd be graphing some massive negative number and then another even bigger massive negative number. It doesn't really show you much of the graph, or at least any of the interesting stuff. So here it gives an example of how to adjust this thing based off the h and k values. Here I have an h value of 1 and a k value of -4. Okay, so with those two things, it's going to shift the graph. It's going to shift the graph 1 to the right and then 4 down. So if I were to graph this thing as like y equals 3 times 2 to the x, you can write the little dot in there. You can use parentheses around it. Either way, it doesn't really matter. Just make sure it doesn't look like it's a 32 sort of thing. So use either the multiplication dot or parentheses. So looking at this here now, I'm saying, okay, well, if I had this, this would be the first one here. So I'm kind of drawing this in purple. And then we're saying, okay, well, let's make the shift. Our h value goes, again, 1 to the right. K value is 4 down. So for the points that we do, 1 to the right, 4 down. 1 to the right, 4 down. That's one way of doing it. I personally don't like doing it that way, but if you want to do it that way, go for it. So again, just start with the parent function and then make your adjustments. Otherwise, we're going to set up our t-chart. Same as we did before. We're going to set it up. Here, my t-chart's going to be a little bit more interesting in that I'm not going to start like at 0. So since my h value is 1 here, I'm going to start at 1, go out to 2 and 3, and then go down to 0 and -1. When I plug in -1, I'm going to have -1 minus 1, which is going to be -2. 2 to the -2 is 1/4. 1/4 times 3 is 3/4. So 3/4 minus 4 is -3 and 1/4. So if you want to do, again, it's decimals and use 2 decimal places, -3.25, that's fine as well. So now we're looking at this thing and we're saying, okay, well, let's look at 0. 0 minus 1 gives me -1. 2 to the -1 is 1/2. 3 times 1/2 is 3 halves. 3 halves minus 4. Oh, in my head, let's see. 3 halves minus 4. No, it's too late. I don't feel like doing that. So this is negative. So this would have been 8. So we got 5 halves. So -2.5. For my 1 value, we already said what this is going to be. This is going to be h, comma, a plus k. So h value here is 1. And now when I plug the 1 in, it's going to be a plus k. A value here is 3. So a equals 3. K value is -4, so this is going to give me -1. Now when I look at 2, Here I have 2 minus 1 is 1, 2 to the first is 2, times 3 is 6, 6 minus 4 is 2. The last one here we got 3, 2 squared is 4, 4 times 3 is 12, 12 minus 4 is 8. And we're good to go. So when we're looking at all these points, again, same process, it's just now, we're shifted a little bit over to the right here. Let's talk about domain and range real quick. Starting with domain, my domain for this thing is all real numbers. So it doesn't matter what I want to plug in for my x's. I can plug in anything, right? Plug in a huge negative number. Okay. Plug in a huge positive number. Okay. That's fine. No problems there. My range, though, is going to be restricted. The range is going to go one of two routes. If my a value is positive, it's going to be everything y is greater than or equal to whatever the k is. My k value here is negative 4. So my range is everything greater than or equal to negative 4. Now, if this was a negative 3 instead, this range would be flipped and it would be y is less than or equal to everything. Oops, actually this should be a strictly less than. And it should be a strictly greater than. Because it won't actually equal the negative 4 or positive 4 until you get to infinity. So we say it's strictly greater than negative 4. And again, if this a value was negative 3 instead, then it'd be y is less than negative 4. Let's write the asymptote here. Asymptote is going to be y equals negative 4. So again, when we're writing the asymptote, it is an equation, right? It's y equals some number. So don't just write negative 4. All right, so here's actually how we use these things. So here we have an exponential growth model. This is basically saying the end value y is going to be the start value times 1 plus the rate. If my rate is a growth rate, then my r is positive. If it's a decay rate, then my r value would be negative. So a growth rate would be like 5%. A decay rate could be 5%. But the difference is that with growth, r equals 0.05, and with decay, r equals negative 0.05. And then here I have t. So t is just going to represent the time. So this could be over months, years, whatever. It'll vary in the problem. Typically it's done annually, and then sometimes there's adjustments to that. Like if I'm doing semi-annually, then I'm doing it twice. But we'll get to those details in a minute here. So let's look at this first one. So in this first example, we start with January 93. There's about, let's start with this. All right, so that's the number of internet hosts in 93. So, just over 1 million. So when we're looking at these things, we're saying the rate increased by about 100% per year. So the rate increase here, oops. Actually, let's grab this colorful thing and we'll stick with all the same colors. Oops. Good to be consistent with it, so. All right. So I'm going to start with my 1313000. Here we go. And now I'm going to multiply by, I haven't used orange here, so I'll use that for my general notation stuff. It's going to be multiplied by 1 times, which should be 1 plus r. My r value here is 100%. So it's a little bit weird to say it's going to increase by 100%. What that basically means is doubling. And we see that by doing 1 plus 1. So here I'm going to get a 1, 100% per year. 100% is 1. So that's where it's coming from. If it was 50%, I would do 1 plus 0.5. So anytime you want to go from a percentage to its decimal, just divide it by 100. So 100 divided by 100 is 1. That's why we're doing plus 1 here. So now I'm going to say to the time, And so now here we read through the problem, we say, blah, 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 write this model, blah, 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 t for time. Okay, cool. So most often, this is going to be the variable in the problem. Sometimes it'll change. Sometimes it'll say, okay, what's the rate to get to this point? But typically that's a little bit higher level. So maybe comes up for now just as like a shout out from me, but we're not going to see a ton of that yet. And we want to figure out some ending value. So again, this is just going to be y. So y equals 1.3 million, approximately 1 plus 1 to the t. So we can simplify this thing, and we could just call this y equals 1313000 times 2 to the t. So again, this is just my starting. This is what it's increasing by every year. So now when it says, okay, graph this model, sure, it's crazy huge numbers, but we could do it. And then use this graph to estimate the year when there were 30 million hosts. So, I'm saying, okay, cool, we can graph this, throw it in Desmos, whatever you want to do, and then find the line y equals 30 million, see where they intersect. Oh, it looks to be right about here, so, call it approximately 4.5 years. So that's the gist of what this is doing. I'm going to leave this at that for now instead of plugging in all the numbers, just because I don't want to hyper focus on this, just because the numbers are big, and other than that, it's fairly uninteresting. Changes it from talking about in millions. So instead of this being written out, it would just be 1.313. So it makes the numbers a little bit nicer there, at least. Here is the holy grail. The reason why I got into teaching math is hopefully so I can help you guys out with this stuff. Compounding interest is interest that is paid on top of the interest which is earned. So basically, if I invest $100 and that investment is earning 10%, the first year that it's invested, it'll earn me 10% of 100, which will give me $10. At the end of the year, my new investment, I should write this stuff down so I'm not just saying it all, right? So say I invest $100 and I'm going to do it at 10%. So $100 at 10%. At the first year, it's $100. At the end of that year, it's 110, right? So this has earned 10% to get me down to here. Now the next year, I'm going to earn 10% on my 110. So now I'm going to earn 11. So now I'm at 120. Oops, no, not 120. 121. So 11 on top of this 110. So here, I can see that my growth rate from here to here was that I increased $10. From here to here, I see that now I have increased $11. I haven't added any additional money. It's still earning a constant rate of 10%, but this is the power of compounding interest. This is how rich people get rich. It is very rare that someone earns the amount of money they do solely from their job to actually reach, whatever wealth they, accumulate. So this is how investments works. This is how retirement works. This is basically how you save for money later on. So very, very important concept here. We talk about this as an annual percentage, but this can be broken down. So this can be broken down into semi-annually, which happens twice. We can talk about monthly, which would happen 12 times a year, weekly, 52 times a year, or maybe we'd even talk about it daily as 365. So when we're talking about this thing, this is going to be our formula. This is our guiding point here. So this A is the amount that it will accumulate to. P is referred to as P because it is the principal investment. This is the beginning amount of money, right? So this is beginning money P, ending money A. And that's going to be multiplied by 1 plus R over N raised to the NT. So this is weird and people are uncomfortable with this, and this is because instead of it only happening once a year, maybe it happens more than once a year. So let's run the same scenario, but now I'm going to do it for semi-annually. So when I run this simulation semi-annually, I'm going to be having my $100 that turns into, and now instead of growing at 10% every year, my 10% is going to happen twice. So every time it happens, now it's happening at 5%. So my 100 is going to become 105. And then my 105 is going to become, and now is where I have to fix my arrow, but also use a calculator. So 105 times 1.05, here we get 110.25. So right now we already see we've earned more just from having this thing compound more frequently. So I'll say it one more time. If this is happening on an annual basis, at the end of the year, I'm getting my 10%. Cool, I'm happy with that. But if I have a choice, whether it's going to earn 10% annually or 10% semi-annually, I'm always going to choose the semi-annual. The more frequently that this compounds, the faster the interest is able to grow on itself. So I'm going to continue doing this out so we see a full 2-year comparison. So now I'm going to do the same thing times 1.05. So this brings me to 115.7625. And then our last time here brings us to 121.55, which may not seem like a ton for us right now, but I promise you that as this stuff builds over years, and when we're talking about a lifespan of investing, we're talking about, maybe you start working at, 25 and then you retire at 65, that's 40 years, right? So when we're looking at these things, we're talking about a great amount of time, which these little differences do really, really start to add up. So when we're looking at this, we can clearly see that the semi-annual compound is better, right? My 10% compounded semi-annually, which means my end value is 2, is going to be better than when my end value up here was 1. So that's what this formula represents. And we're going to look at a few different examples of that. So rather than look at my messy handwriting, let's take a peek at this. So here we're going to deposit $1,000 into an account that pays 8% annual interest. Now that 8% annual interest is what's referred to as the nominal amount. Okay, so that nominal percentage rate is basically saying this is what it is for the year, but the actual rate is going to be different depending on how frequently that it compounds. Annually will actually be 8%. Cool, only happens once. Quarterly is going to end up being a little bit higher, and daily is going to be even higher than that. So I just want to check to make sure. Yeah, I include all these compounding interest amounts. So when we're talking about these things, I do have them referenced here. Annually is 1, semi-annually 2, quarterly 4, monthly is 12, daily is 365. So when we're doing these things, just keep in mind these are the most common, but they're not exclusive. I don't know, say I had like a really wacky investment and it compounded 17 times a year. Okay, whatever, right? My end value is just going to be 17. So just keep that in mind. Let's jump back here. So looking at the first one here, we have the amount that it will accumulate to is going to be equal to my starting amount, which is 1,000. So I'm going to highlight that for all these ones here. And now let's get into the interest rate. Okay, so this is 8% divided by 1. This 1 is coming from this happening annually, okay? So annually means I have a 1 here, and I'm doing 1 times 1 because this is going to happen for 1 year. So this year part is staying constant for everybody. So this is 1 year, 1 year, 1 year. The end value is different though. So here 0.08 divided by 1, well that's just 0.08. So 1 plus 0.08 is 1.08. 1.08 raised to the first is just 1.08 times 1,000 gives me $1,080. Sweet. So at the end of the year, I end up walking away with $1,080. Pretty cool. But what if this thing compounded quarterly instead? If it compounded quarterly, looking at this one here, I'm going to take that 8% and I'm going to divide it by 4 within the parentheses before I add it to the 1. 0.08 divided by 4 is 0.02. 0.02 plus 1 gives me this 1.02 here. And now I'm raising it to the 4th. 4 times 1 is 4. So that's where this is coming from, and that's how I get this 1.02 here. Now I'm doing 1.02 to the 4th, which ends up being 8, 0.243% or whatever. And now I have that times 1,000. So that's going to give me 1,082.43. Third one here is daily. So daily is going to be even faster. I'm going to do my 0.08 divided by 365, which gives us approximately this number here. When I do these, I'm going to evaluate the entire thing on the calculator at once. So I'm not trying to like break it up and do one piece, round it, do another piece, round it. That's how we introduce more and more rounding error. We really want to force the calculator to do all the work for us, and then we only round as a very last step. So I would literally have this entire thing punched in as is on the calculator and just hit enter, and then I would round my final answer. And that's with our daily interest rate here. We see it's going to give us the highest amount because it's compounding more frequently. Here we have compounding interest. So here's just this same formula, the amount that it's going to accumulate to, principal, rate, time, period, which is just the number of times that it compounds, all the different options here, or at least the ones we'll see most often. Then I have 3 examples here. So here we're choosing a fund to invest for 1 year. Fund A is at 5.55% annually. Fund B is at 5.5% semi-annually. And then Fund C is at 5.45% daily. Now, before we knew what this, compounding did, we may have said, oh, A is a clear choice because Fund A here is going to have the highest interest rate. Well, it's true. As a nominal rate, it is the highest. But since this compounds semi-annually, it's actually going to end up beating out this annual rate. And if I look at the daily rate, it's going to even beat out that semi-annual rate. So even though I have these values here, I'm going to end up looking at the daily for the choice that I would invest my money in because it's going to compound to me the most over a year. So again, more numbers just plugged in here, showing you another example. Here we have another example where I'm depositing $1,000 into an account that earns 5% annually. How much will it be worth in 7 years? So 1,000, 1 plus my 0.05 raised to the 7th gives me this amount here. If I did the same thing semi-annually, we see the value right here. Here I would like to save up for a jetpack. I've always wanted one. Cost 10 grand, so I finally feel like it's within my reach. And now I have 8 years to do so. So how much will I need to invest now into an account earning 11% compounded quarterly to be able to earn that money, right? To enable me to buy that jetpack. So here I'm trying to solve for P. I know that it costs 10,000, so now I just need to solve for this value. So I would pretty much just take the 1 plus, now here's my 0.11 divided by 4 raised to the 4 times 8. This is 4 times, which is compounding quarterly, times 8 years up here. So I would take that value, which comes out to be approximately 2.38, and I'm going to divide by both sides, and I get my p-value to be approximately $4,197.41. So if I took this amount and invested it now in 8 years' time, I would have my $10,000 and I'd have my sweet jetpack. And that is it for today. So we'll leave off with the jetpack and we will get into exponential decay tomorrow.